Good afternoon, everybody. Let's get started. So for announcements, homework 5 is posted. Take a look at that due date. That's on Canvas. We're going to start lab 8 this week. This is going to be the inertial measurement unit lab. So you're going to be able to measure roll, pitch, yaw on your aircraft test bed this Friday. So we're going to start working on that. And then coming up on Monday, 11/4, the second exam is going to be issued, and you'll have a couple days to work that. It'll be due on Wednesday, 11/6. I'll send out an announcement on that, so you'll know that's coming up. You'll get a Canvas announcement about that. So last time we talked about microcontrollers. We actually finished up microcontrollers talking about timer, peripherals, and interrupts. And so today we're going to start on electronic sensors. So I like this topic because it connects the electrical world with the physical world. Lets you do a lot of interesting applications. I want to zoom out for a second to show you where we are in the course. So remember, the objective of this course is to cover a wide range of electronic systems topics. And many of these topics impact or apply to non-electrical engineers. So remember, I showed this diagram, and we've been working in the areas so far of controlling power, power sources, power conversion. You've been controlling an electromechanical device in lab. We're going to get to communications, but now we're going to talk about sensors. So we're going to talk about light sensors, including infrared sensors, temperature sensors, strain gauges and accelerometers and gyroscopes, magnetic field sensors, and current and power sensors, or how do you determine, let's say, power delivered to a device using sensors. So we're going to dig into these topics and talk about how the sensors work and then how to use them. Okay, so I think having a basic knowledge of how they work will help you decide what kind of sensor you need for your application, and then how to use them, just basically how to connect them in a circuit and get them to work. Okay, so we're going to dive into electronic sensors. I'm going to give you an overview. These are commonly used in electronic and mechanical systems, mechatronic systems. They're commonly used in product testing or requirements verification, and also applied research. So if you're measuring something physical and you're trying to prove out a concept, then you might use sensors. I put these images out here because, well, I just think they're cool. Here's this was what was this? I forget which aircraft this is. I think it's a Boeing. With its wings bent up, you can be sure there are strain gauges on there measuring places along that wing spar and that airframe. I like this picture at the bottom because this is an SR-71 engine. I just love how it glows. But you can imagine there are a lot of sensors attached to this to capture the data during these tests. So, but going to the little less dramatic world. So why understand electronic sensors? Why would you want to do this? Well, basically because electronic sensors support mechanical system development and applied research in mechanical engineering. So I think it's good for mechanical engineers to know what's available when you want to verify something about your mechanical product or research area. So sensors are applied in mechanical system control, engines and propulsion, like weather monitoring, and every kind of experiment you could think of. So I mean, it's just a wide range of areas where sensors apply and where you might want to capture and log the physical behavior of products and projects. Okay, so electronic sensors are used in control systems, just like you're using the sensor in lab for propeller speed, for monitoring experiments as they progress over time, and also for built-in test. We talked a little bit about this in lab, but built-in test is important for systems when, even if you have a deployed product and you want to collect maybe diagnostic data you can or alert a user that hey, something's wrong, like a check engine light on a car, right, or some other product. Um, Built-in test is usually important for when you start up a product or as the product is running. So many applications. So we're going to discuss several common sensors that I think apply to mechanical systems and otherwise electronic devices that are connected to mechanical systems. So we're going to cover what they do, how they work, and how to use them so that you can apply these in the future. We're going to talk about temperature sensors and light sensors and Hall effect sensors that sense magnetic fields, strain gauges that you can use to measure weight or acceleration. We'll apply that to accelerometers and gyroscopes, and we'll talk about measuring voltage and current so that you can calculate values like power delivered. Okay, I'd like to bring up aircraft instrumentation as an example for sensors, not just because I like aircraft, but because there are many measurements and outputs of sensors that are converted to different units and sense different parameters that are important to flight. And they show a tie back to, well, just the basic sensor itself. For example, aircraft attitude, right? Aircraft attitude, roll, pitch, and yaw. That ties back to a gyroscopic sensor, which you'll see also ties back to a strain gauge, or that theory for a strain gauge anyway. Airspeed. Airspeed's important. That's an air pressure sensor that also ties back to a strain gauge or equivalently a load cell with strain gauges. Altitude. Altitude is another air pressure sensor, right? If you deflect a diaphragm because of air pressure, you can measure the deflection using, well, a strain gauge. Heading, that's a magnetic sensor to measure the Earth's magnetic field and the direction of north, so you can figure out heading. If you look at engine instruments, then manifold pressure. Manifold pressure is the pressure in the intake manifold of an engine. There's another pressure sensor. RPM, that's often a magnetic sensor to figure out the rate at which a crankshaft is spinning. Fuel flow sensor, that can be another impeller-like sensor that, again, is another magnetic sensor. So I point these out because you don't usually think of, well, how do I measure fuel flow or any fluid flow? You wouldn't think automatically of a magnetic sensor. You wouldn't think I have to know how magnetic sensors work and what sensors are available for this, but you know, tying this to the real physical phenomenon. Exhaust gas temperature, cylinder head temperature, those are thermocouples. We'll talk about different types of temperature measurement sensors. Oil pressure, there's another pressure sensor. Fuel quantity, that could be a resistive sensor with like a float on it or a magnetic sensor. It actually can be a capacitive sensor as well. So these, when we're talking about these basic sensors that measure, weight and magnetic field, or light, there's another level of parameters that can be measured on top of that using those basic sensors. So I just wanted to point that out here. So let's look at a typical electronic sensor application. So you have some kind of product, some kind of system, some operation in a factory, or some natural phenomenon that you're trying to measure, right, on Earth or in space. And you're trying to measure a physical quantity. And so there's some physical quantity. It could be heat, it could be vibration, it could be displacement. And you're trying to get that, well, onto a hard drive or onto paper. You want this collected data or some kind of control values so that you can build a control loop and control the process if this is, let's say, some kind of operation or process over here. All right, so to do that, to sense that physical quantity, that's where we put the electronic sensor in. And that's the basic device we're going to use, and there are going to be circuits that support that. So the electronic sensor converts that physical quantity into some kind of electrical signal, usually a voltage or a current, and often not in what I call a usable range. In other words, that voltage might be microvolts, or that current might be microamps, or maybe it's just millivolts, but you don't have a voltmeter that's accurate enough, or you have maybe a noisy environment, electromagnetically noisy environment. So the sensor output may not be big enough or usable to measure directly. So often near the sensor, you have to have some kind of signal conditioning. So when I say signal conditioning, I mean it's a circuit that has an input and an output, and oftentimes it has gain. That means it multiplies the input by maybe a constant value to produce an output, right? Make the signal bigger. You might have to have an offset, right? If you have a analog to digital converter that only measures positive voltage, and you have an AC signal or a varying signal over time that goes negative, you might need to apply a DC offset. You might have to convert current to voltage. Oftentimes, if you have a current, maybe a small current from something like a photodiode, maybe microamps of current, and you have an analog to digital converter that measures 0 to 5 volts voltage, then somehow you have to convert that really small current into a reasonable range of voltage to be measured. Okay, so all of those operations, those functions I'm calling signal conditioning. And that puts the voltage in what I call a usable range, something that can be measured by a voltmeter or a data logger, like a voltage data logger, or a microcontroller with an ADC that is going to read that voltage and possibly have some kind of feedback control, right, to control the process. You know, you might have a closed loop control like we're doing in lab. You might have some other kind of feedback that is just telling a process to maybe turn on and off, like a thermostat in a heater. Or you might have some kind of alert. Maybe you're going out of bounds of a normal operation or out of safety limits. So you might want to have some kind of alert. So here is where sensors fit in, right? These electronic sensors. So we're going to talk about, you know, signal conditioning and voltage measurement. And again, this is kind of what you're implementing in lab. But we'll dig into the details of the sensors to show you basically how they work and how to use them, especially for the sensors you're not using in lab that you may want to use in the future. Okay, so to capture data on that physical quantity that we want to measure, we need to sense, condition, and measure the electrical quantity, which is usually voltage. And that somehow translates into the physical quantity. So we're going to convert that captured voltage, that measured voltage, logged voltage, into the units of the physical quantity, right? You may have 50 millivolts is some temperature in degrees Fahrenheit, degrees Celsius, right? So that's what we're going to talk about here. Okay, so let's talk about measuring that voltage. So now you have a sensor, you have signal conditioning, and you have some kind of reasonable voltage that you can measure. Sometimes you can just use test equipment, right? You can collect voltage manually or using data acquisition software, using benchtop voltmeters or handheld voltmeters that have, you know, you can read the screen, or you can have some kind of data acquisition software connect to them. And then you're going to convert that voltage to the physical quantity units, like manually using a spreadsheet. Maybe it's your data acquisition software. And then you'll use or analyze that data in the physical quantity units. But since we just finished up talking about microcontrollers, oftentimes you'll do the voltage measurement with an analog to digital converter and a microcontroller or a microprocessor, or otherwise some kind of digital system. Right, so you have some kind of usable sensor voltage coming into your microcontroller or microcontroller board. You'll store that on disk in memory, or process it in real time or near real time. So you might have some automated application that periodically or on a trigger samples voltage, and then the software can convert from the voltage to the physical quantity units that are important to you. And then you can log that data to just post-process later or react and respond. Right? So the point of this discussion, the point of the following topics is to show how to use the sensor and measure a physical quantity and produce a usable voltage so that you can do that conversion to the physical quantity units. Okay. And so that's what we're going to talk about. And you've seen that in lab. You've seen how you're sampling time between blade crossings, and you have a counter in microseconds, and then you're converting that to a rate that represents the RPM of a propeller in revolutions per minute. Okay, but it all starts out with a sensor. Okay, so let's go lower level into those sensors. So here's the roadmap of sensors we're going to cover. We're going to talk about temperature sensors and different types, when they would be used. We're going to talk about light sensors, again, different types, magnetic sensors, how they work and where you might use those. We'll talk about strain gauges. Those are probably of most interest here to mechanical engineers. We're going to talk about accelerometers and gyros, and then current and power. All right, imagine how if you you had a current sensor on your project right now to figure out the voltage delivered to the motor, right? You know the duty cycle of a pulsed voltage. If you knew the current, then you could figure out how much electrical power is delivered to that motor and get a good measure of how much physical power, mechanical power is being delivered to the air, really, to push the aircraft forward if that were an aircraft. So let's start out with temperature sensors. Okay, we're going to focus on each one of these. So there are different types of temperature sensors, different ways to measure temperature. I'm going to talk about 4 common types of sensors that I've seen in typical circuits. So we're going to talk about semiconductor-based temperature sensors in different packages that look like this. This one on the left should look familiar. That's like the one you're using in lab. There are surface mount chips that do the same thing, that tell you the temperature of the circuit board or the environment around the circuit board. We have thermistors, and those are low cost, common. We have thermocouples. You'll often see those come with voltmeters that have temperature measurement capabilities. And you'll see, we'll talk about resistance temperature detectors, usually just called RTDs. So we'll cover the principle of operation. So the principle of operation of a semiconductor-based temperature sensor is that the voltage across a PN junction, and it's usually in a transistor in these devices, it varies linearly with temperature. So we can get some measure of absolute temperature out of these devices. You'll see these used in general temperature measurement, just thermostats, circuit board temperature measurements, cooler controllers, air conditioners, things like that. And you'll see these also built into on-chip monitoring. So some chips get really hot because they consume a lot of power, maybe if they're doing processing. And like, for example, your microprocessor in your computer, or your often microprocessors on boards, they have built-in temperature sensors so that you can see, are you going to overheat the chip or not? So there's some diagnostics and monitoring in there. So maybe you have to back off on the processing rate or the clock rate to not destroy the chip. So these are often used in those applications. So thermistors work on this principle. The resistance of these materials, this thermistor material, it changes greatly with temperature. Greatly is relative, but it changes enough to get a good temperature measurement when resistance of that resistor changes. I mean, I often like to say thermistors are just really bad resistors, right? Because normally you want a resistor to maintain a constant resistance over temperature. So maybe the gain in your op amp circuit is constant over temperature. But these resistors, these thermistors, are designed so that the resistance changes greatly compared to regular resistors over temperature. And these are again used in general temperature measurement. But another application I'll show you is for current limiting. Okay, so they act like a natural current limiting device. I'll show you that. You know, if you have a device where you don't want too much current going in because something's wrong if too much current is going in, you can limit the current with these. Thermocouples work a little differently. They work on this principle: the temperature difference across two dissimilar conductors, meaning two different metals, they produce two different voltages. So the two conductors, the voltage across those conductors, when there's different temperatures on each end, I'll show you, they produce two different voltages. You could take that voltage difference and figure out the temperature. And that's called the Seebeck effect. Okay, so these thermocouples are often used in harsh environments, but you can use them in benign environments. But I've seen them used in exhaust pipes to measure exhaust gas temperature, or just really any hot gases. That's common, or even in flames too. And they're used in thermostats to control heaters or temperature control loops. And then there are resistance temperature detectors. So these devices use a very fine, very thin wire that have a really small resistance, but it's an accurately measurable resistance that changes over temperature. Okay, so you'll see these in, if you have a pellet stove, like a pellet smoker, you'll see something that looks like this sticking out of the side of the, I guess the side of the grill. Often they use RTDs to measure the temperature inside, and industrial processes will also use these RTDs, right? So, but let's dig in. Let's start with talking about the silicon-based temperature sensor and how they work. So if you have a transistor, uh, the base to emitter voltage, VBE, changes with temperature. By this equation right here, this is what describes it. So K is Boltzmann's constant, T is the temperature, IC is the collector current that you can control through the transistor. And then this reverse saturation current, this is the current that changes with temperature. Right? So this I sub S changes, and that's going to cause a VBE change. And so what you can do is you can actually use two transistors, and you have these two currents, I1 and I2. So if you look on the right here, you can have two current sources that are controlling I1 and I2. And so those are identical transistors. So they might be made on during the same process on the same die for the same part. So those transistors are as identical as they can be. And then you have these two currents, and you measure the difference between VBE1, transistor 1, VBE2 to obtain an accurate temperature measurements, right? So you have two different currents, VBE1, VBE2, measure those, measure that voltage difference, and you can get a temperature difference, right? Here's the relationship. The delta of VBE between those two transistors is this, and you know I1, you know I2, you have Q, the electron charge, and there's T. Okay, so you can calculate that. So the voltage difference between two identical PN junctions that are operated at two different current densities, right, this is going to give you a value that is proportional to absolute temperature. So that's what your chip is doing, your little TO92 package that you have connected to your project is doing in lab. This is the voltage out of that amplifier that you're seeing. So let's take a look at how to use them. There are two different types I would consider, an analog output and a digital output. So here's an example of an analog output part. This is similar to the one you have in lab. in this TO92 package. But there are also surface mount components. So you could put this on a circuit board, either on a main circuit board, or you can put it on maybe another separate board that you're going to mount someplace else as a remote sensor. But you can get these in different packages. And here's a schematic of what's inside. So here are your couple transistors here. Right? You have a current flowing down, and you have an amplifier and an output stage. Okay, so the V out here, it's designed to have 10 millivolts per degree C. That's the slope of the voltage with respect to temperature, plus an offset here. So to use these as you're doing in lab, you sample the output voltage with an analog to digital converter and read that with a microcontroller. Or again, you could measure this with a voltmeter, measure the output with a voltmeter and tell the temperature. And then you amplify and offset if needed to match the span of the ADC. All right, so you should be familiar with that by now, but there are temperature sensors that are digital outputs. They provide digital outputs. So here, well, if we go to the left, let's go back to the left. The analog output device, you apply power, VDD, ground, and then V out with respect to ground is this voltage that represents temperature. For the digital output device, you apply power, you apply ground, and then you get this data output. So the data output will have bits that come out in serial form that give you different values, and you can read those values with a microcontroller that has a matching serial interface protocol. And oftentimes you can find a software library function that reads that protocol. And definitely for the Arduino, if you can find a temperature sensor with the digital output, you could probably find a library that will just read that without writing low-level code. Okay, so for analog sensors, apply 5 volts, apply ground, read the ADC input with a microcontroller, make sure you have a common ground. And here's the plot of voltage out of the device versus temperature. Right, so the device that we just talked about, this, and I gave the equation for it, this is the 10 millivolts per degree C. That's a common slope. You can find many parts that give you that slope. But if you need higher sensitivity here, you can use this 20 millivolts per degree C. So there's another part number in this family that gives you 20 millivolts per degree C. So it's a little more responsive to changes in temperature. All right, and this is another device. This is the device that you have in lab. So you're doing the same thing, and you can see this this device has the 10 millivolt per degree C and actually 2 different flavors with 2 different offsets, and as well as the 20 millivolts per degree C. So you look at the data sheet, you look at the characteristic of output voltage versus temperature, and you select your device for your application based on the range you need and the sensitivity you need. But they're nicely linear devices. And you can apply correction to those if you need to get more accurate. Okay, so the digital sensors, this is the internal diagram of this one DS18B20 device, right? It looks just like the package that you have in lab, but it's totally different inside. So on the left, you apply power, VDD, you apply ground, and here's the data line. Here's a pull-up resistor. You know what that is now, right? So that 4.7 k ohm resistor pulls this line up to the VDD value usually, and then either the microcontroller connected to it or this device will pull low when it wants to apply a 0 to the line. Okay, so you can see there's here's the actual temperature sensor. It's the small box over here. And then there are a bunch of digital peripherals here, right? So there's you can trigger an alarm based on a program temperature. You can program that temperature from your microcontroller. You can set a high or low trigger there. There's different configurations that you can set. And then a data check here, 8-bit CRC generator, checks the integrity of the data that's going back and forth. Make sure there are no errors in what you set or what you read. And so it's more complicated. So probably one of the reasons we're not using it in lab, it would take a little more time to get this working. And you've got to use, in this case, what they call the one-wire digital interface. Using a digital port, you're going to read that. Okay. And then over that digital serial line, the temperature is communicated in this digital word. Okay. And I say this would have taken longer to do in lab, but the Arduino has libraries that read this bus. So you can grab the one-wire bus library, and you can actually grab this interface chip, this temperature sensor chip's interface protocol. And so you don't have to dig into the data sheet unless you need to use some of the lower level functions that aren't available through the library. So I encourage you at some point, if you have a project that needs temperature sensing, give this part a try, or any similar part that has digital sensing. What's nice about it is, let's suppose you had to locate this device far away from the microcontroller, even just a few feet away from the microcontroller. If this were an analog sensor, you'd have a very long analog wire going back to the microcontroller, between the microcontroller and the sensor. And that's an opportunity for loss in the wire, even though it's not that much current, or probably more importantly, electromagnetic interference getting on the wire, right? If you had it near like a fluorescent light or a pulse width modulated LED or something like that, you might get inaccurate measurements of voltage because of the interference. In this case, that you have a digital interface, if you had a very long wire to the sensor, as long as those bits make it back with good integrity back to the serial port of the microcontroller, the values aren't going to be wrong. So I would say, you have a better chance of getting a more accurate measurement with this digital interface. All right. All right. So that's the first of the temperature sensors that I wanted to talk about. The semiconductor-based temperature sensor. Let's move on to thermistors and talk about how they work. So you'll see a couple kinds. A negative temperature coefficient, NTC, thermistor. And so for NTC thermistors, the resistance falls as temperature rises. And so these are semiconductor-based metal oxides, the materials that are used in there. And it works like this: increasing the temperature of a semiconductor increases the number of active charge carriers. So if you have more charge carriers in your semiconductor, it's going to look like it's going to be a lower resistance. Okay, so that's the NTC. Remember, NTC resistance falls as temperature rises. And you might think, well, wait a minute, wouldn't it be easier if we just had like resistance go up as temperature goes up? And yes, there's a version that does that, but I'll show you why it's not such a good idea to use these as temperature sensors. This positive temperature coefficient thermistor, PTC, its resistance rises as temperature rises. And it's a doped polycrystalline ceramic material. But the good thing and bad thing, depending upon the application, is that the resistance rises suddenly at a critical temperature. So if we plot these two, the NTC and PTC, on a plot that shows here's resistance on the left, and this is temperature. So this is resistance versus temperature. So the NTC is the blue line here. And you can go look at this website. You can see lots of information here on this. I grabbed this plot from there. So you can see that for NTC, this is as expected. As temperature goes up, resistance goes down. And this is a log scale here. So it's not linear, but So as temperature goes up, resistance goes down. But you can see it's nicely behaved. You can map a resistance to a temperature, right? It's a function. It maps nicely here. Um, and you could figure out some way, and we'll talk about how to detect or to figure out what is the resistance, or at least make that changing resistance produce a changing voltage so that we can measure the voltage and relate the voltage to temperature. PTC, right, is this. At some point, you see this rapid rise at this critical temperature. So here at this point, above, 50 C here, the resistance goes up as temperature goes up. Okay, but as a temperature sensor, it's not very well behaved because you could see here, well, wait, this is a negative slope. The resistance is going down at some point, just slightly, because this is 1 ohm right here. This is really low. Resistance is going down, and then at some critical temperature, it goes up at some very high temperature. Okay. So you wouldn't want to use this as, you wouldn't want to use a PTC thermistor as a temperature sensor, like in these ranges, because you're not changing much resistance over temperature, and it's going the wrong way for a PTC. And then if you look at 1 ohm, right, you cross 1 ohm here, you cross 1 ohm here, so it's not a function, right? It's not uh, you can't tell at what, well, it is a function, but you can't tell at 1 ohm what is the temperature. Is it somewhere over 75 C, or is it somewhere below 0 C? So mainly NTC thermistors are used as temperature sensors. So they're well behaved. They're good for sensors. PTCs have this sharp rise, and they're actually good as uh, current limiters. So because of this sharp rise in resistance with temperature, the PTC, if it has a lot of current going through it, it has a self-heating effect, so that thermistor itself gets hot. As it gets hot, the resistance goes up, it gets hotter, and the resistance goes high, so it stops the current. So you can use these PTCs as current limiters in a device. Okay. All right. So here, so there are various types based on the temperature range. You can get different part numbers based on temperature ranges, the response times, and the environment. You can get these in different packages, like glass encapsulated thermistors that can withstand harsher or damp environments, beads, discs, different types of different costs and different ranges. All right, so uh, let's talk about how to use them. So you have this device, two-terminal device that changes resistance with temperature. And so you have let's say you have a negative temperature coefficient thermistor. There are various ways of relating temperature to resistance, and it depends on the accuracy needs. It depends what you're using to actually measure whatever electrical quantity you're using to relate to temperature. Um, but you can use tables of resistance versus temperature out of the manufacturer's data sheet, or you can use the beta for the thermistor. So the beta is this value right here that's often given in the data sheets as either a value or a table, usually a table. Okay, so here you have R1. This is a reference resistance at some temperature, T1. So that's like maybe 25 C or a value in Kelvin. Okay, so that's T1. And then you get then you have resistance R2. That's the temperature of the resistor, of the thermistor. Okay, so you can relate T1 to T2 based on R1 and R2. And these values are given in datasheets. So beta, R1, and T1 are given in the datasheet. So R2 is something you'd measure. T2 is something you'd calculate to figure out what the temperature is. So here's an example. This is a table here of the R25 value. So this is the nominal resistance of the thermistor right here at 25C. And then you could see the beta value here. It's listed as B. All right. And that reference temperature here is 85. Okay, so 25 and 85. That's C, not Kelvin. So this approach is useful over a relatively narrow range because beta is actually temperature dependent. So over a 50-degree span, you might expect a 0.3 C error. That may be good enough, maybe not. But you can also use tables of temperature versus resistance to figure out the temperature based on resistance. One simple way to output a voltage versus temperature so that you could sample with a microcontroller is to use just a voltage divider, right? You have a fixed resistor and then your thermistor here. And use the voltage divider formula here. Vs is some voltage, maybe like a 5-volt voltage that is constant. And the thermistor value changes, that resistance changes. R1 would be constant. Okay. And then sample with a microcontroller. So that's a way you can measure, you get a measurable quantity of voltage that you can sample with an ADC. And so you're not really directly measuring the resistance of the thermistor, but the change of resistance gives you a varying voltage versus temperature. Okay, so that's one way I've done this before. So here's a practical circuit example. Suppose you want a circuit that outputs a voltage that indicates temperature, and you've selected a particular thermistor. So you have this thermistor with R25 equals 10K. So this would be called a 10K thermistor, right, at 25C. And you have this beta value here. Okay, so you want to determine the resistance R therm at a temperature T therm between 25 and 85C. So you would use this, right? So there's the formula. You can rearrange that or use an equation solver or however you want to do this. But here's the beta value, and here are the temperature values, right? And so if you plot that, you'll get something like this. So here's the resistance versus temperature. So I know I'm going to have a resistance that varies in that range, kind of this, what did I say, 85C. So it's going to vary between maybe a little over a K ohm up to 10K ohms, right? 10K is the 25C value. So you can use a voltage divider to output that voltage versus temperature as I just showed. Here it is here. That's how you would calculate it. All right. So if you plot the out now, not resistance, but the output voltage of the circuit versus temperature, you'd have this voltage. So that's a well-behaved voltage. You have a value that you could set up your Arduino in lab to measure voltages. You're using a 1.1 volt full scale range. You could change that to be somewhere in the mid 2s or even 5 volts and still get a reasonable measurement here. But you could sample the voltage and then do a conversion, maybe even just by table lookup between voltage and temperature, and you could calculate the temperature. Okay. All right. So any questions on what we covered so far, either the concept of sensors, these basically simple interface circuits we're using right now, or thermistors, before we go on? All right. Okay, nothing heard, nothing seen in the chat. Um, we're about 3.5 minutes before the end. So what I think I'm going to do is I don't want to start thermocouples just yet. We're going to start thermocouples at the beginning of the next lecture. So I'm going to end this lecture right here. If you have any questions, if you want to chat about anything, stop by office hours right after class. Don't forget that the exam will be issued on Monday and it'll be due Wednesday. I'll send an announcement out about that. Homework 5 is posted. Check out that due date and due time. And let me know if you have any questions about that. Check out Canvas for all of the upcoming assignments and activities coming up and lab. And so I'll start office hours in just a few seconds. So if you'd like to join, please join. If not, I'll see you next time. Have a great night.